Hello everybody, and welcome back to Exploring Quantum Physics. I'm guest lecturer Ian Applebaum, and I'll be telling you about the Stern-Gerlach experiment. In the last lecture, we found that incorporating the correct relativistic invariance into the quantum mechanical wave equation, constructing the Dirac equation, not the Schrödinger equation, left us with the requirement that the electron wave function has two components. Our hope is that understanding this degree of freedom will lead to an explanation of the anomalous Zeeman effect, where gas discharge spectral lines are split into more than the three components of a Lorentz triplet. The Stern-Gerlach experiment, the subject of today's lecture, was instrumental in revealing the underlying physics of this so-called anomaly. The experimental geometry of the Stern-Gerlach experiment was something like this figure, where silver was heated in a vacuum so that individual atoms with thermal energy, kBt, of several thousand Kelvin were emitted from a furnace and collimated through two sequential slits. This beam then passed through a region of high magnetic field gradient perpendicular to its velocity. These were neutral atoms, so the magnetic field itself did not affect the trajectory. However, for atoms carrying a magnetic moment, the gradient of the magnetic field will impart a force and deflect the beam. We can predict the observed deflection by first calculating the force. This is just the gradient of potential energy, which we know from the dipole interaction energy. The displacement is given by the solution to the classical equation of motion for a constant force. Using the time of flight, length over thermal velocity, we then have a complete expression that we can use to obtain quantitative values of deflection. For a gradient of about 10 Tesla per centimeter over a distance of 3 centimeters, we predict a deflection of 100 microns for a moment of 1 Bohr magneton oriented parallel to the gradient. If the moment is oriented anti-parallel, the deflection is in the opposite direction. Now, if the magnetic moments of the neutral atoms are distributed randomly upon emission from the furnace as expected from a classical degree of freedom, this deflection will vary continuously and merely result in a broadened beam of width twice d. So what happened? What did Stern and Gerlach actually see? Here's what Stern and Gerlach saw on the glass slide removed from the apparatus after converting the nearly transparent deposited silver into black silver sulfide. On the left is the deposited pattern from the silver beam without the perpendicular field gradient, and on the right is the pattern with the field gradient. Overlaying the pole geometry used to create the gradient shows that the horizontal deflection is greatest in the middle simply because the field gradient is higher there. The length scale shows that this deflection is on the order of our calculated 100 microns. But the most remarkable thing about the pattern with the magnetic gradient is that it is not simply smeared as expected from randomly oriented magnetic moments, but that it's split into two well-resolved beams. This postcard was sent to Bohr and says below something like, "Congratulations on confirmation of your atomic theory." Stern and Gerlach thought that they were measuring the orbital magnetic moment predicted by Bohr's model, but this was 1922, before the Schrödinger equation and the realization that the L equals 0 s states have zero angular momentum. They didn't measure the orbital component, they were measuring the magnetic moment of the intrinsic angular momentum of the unpaired 5s electron. This is rather unfortunately called spin for historical reasons, and the twofold splitting of the atomic beam is due to the two possible eigenvalues of the z component, plus or minus h bar over 2. It's then natural to identify an additional quantum number, the spin magnetic quantum number m sub s, that takes the value of plus minus 1/2. A so-called G factor nominally equal to 2, due to a relativistic effect called Thomas precession from Lorentz boosts, must be included in the conversion from angular momentum to magnetic moment. We therefore identify the two components of the electron part of the Dirac wave function as the amplitudes of spin up and spin down. For those interested in the serendipity behind this experiment and the historical development of the correct interpretation, I recommend this popular account by Friedrich and Hirschbach in Physics Today very highly. Incidentally, long after this extremely important experiment, Stern won the Nobel Prize during World War II, but Gerlach was snubbed, in part because he stayed in Germany to work on wartime weapons development for the Nazis. I said it was unfortunate that the word we use for electron intrinsic magnetic moment is spin, and this is because although it's natural to try to understand how an individual particle can carry intrinsic angular momentum, there's no classical analog to it. Still, one can find figures like this propagating this false notion in textbooks. In fact, the idea of spin was at first ridiculed for the very reason that the geometrical interpretation leads to nonsense such as this. if an electron is a spinning charged sphere, then what's the velocity at the electron surface? We can calculate the classical electron radius by equating the electrostatic potential energy needed to assemble charge E into the sphere with the electron rest mass, and then use it to determine the velocity necessary to generate one Bohr magneton. The result is the speed of light divided by the fine structure constant, a dimensionless quantity equal to about 1 over 137, far less than unity. The velocity, then, would have to be over 2 orders of magnitude higher than the speed of light. Clearly nonsense. This issue played an important role in history. Goudsmit and Uhlenbeck are credited with the correct interpretation of the Stern-Gerlach experiment in 1925 as being due to the intrinsic electron angular momentum, but perhaps only because they were lucky enough to have an open-minded advisor, Ehrenfest, who said, "Well, that's a nice idea, though it may be wrong, but you don't yet have a reputation, so you have nothing to lose." Whereas the same idea had apparently been suggested several years before by Kronig, who was thoroughly discouraged by his mentor Pauli, who said, "It's indeed very clever, but of course has nothing to do with reality." Llewellyn Thomas, who introduced the Thomas G factor, wrote a humorous letter to Goudsmit after his paper's publication, saying the following: "I think you and Uhlenbeck have been very lucky to get your spinning electron published and talked about before Pauli heard of it. It appears that more than a year ago Kronig believed in the spinning electron and worked out something. The first person he showed it to was Pauli. Pauli ridiculed the whole thing so much that the first person became also the last, and no one else heard anything of it, which all goes to show that the infallibility of the deity does not extend to his self-styled vicar on earth."